Okay, um, good afternoon. Today's topic is counterfactuals in artificial intelligence. And this is a topic of emerging importance in a couple of ways. One is counterfactuals are useful as a method for explaining the performance of artificial intelligence systems. If an artificial intelligence system used by a bank comes out and says a loan has been denied, it would be nice to get an explanation from the bank as to why the loan was denied. If the explanation is simply based on your own data, such as income, number of dependents, and the job, and so some other factors, age, it's not as helpful as an explanation that goes beyond. It says, based on your data, if your income was about $10,000 more than what it is, you would have got the loan. That's kind of a counterfactual. It's not the actual fact, but gives you something else where you would make it. That's a counterfactual explanation of a decision by a machine learning system. Another counterfactual was in the case of a doctor who's observed several symptoms and so on, and is wondering whether a particular drug would make a difference. So it has not been given, it is to be given now. Will that make a difference given all the other facts in the case? That's also a counterfactual. So how do we answer these counterfactuals, either for explaining standard AI, that is the standard deep learning AI, or build it into a system which naturally provides such explanations. So we will begin with the motivation of counterfactuals in AI. Then we'll go on to a topic which is a topic in symbolic AI, in probabilistic graphical models, about how queries that are counterfactual can be answered. We know how queries, probabilistic queries can be answered. There is some kind of a standard inference through a Bayesian network where you go about answering any given query saying, what's the probability of this event given that we've observed some other events? These are usually conditional queries. And probabilistic reasoning provides answers. It might be a computationally hard problem, but there are good approximate algorithms and even exact inference algorithms that provide you answers for probabilistic queries. Probabilistic queries could also be answered well by deep learning algorithms, which find probabilistic correlations as the main thing that it's discovering. Then there are causal queries where we are asking, what if if a particular value was this, what kind of an answer would you give to that? So in a causal query, we're usually interested in determining whether there's causality between two variables or there are some hidden variables that make for apparent causality, but it's just correlation that we're dealing with. And causal intervention queries allow you to determine whether there is real causality or it's only correlation. So that's a simple idea of causality. The more complex scenario is the third one, which is counterfactual, where we have a situation of the facts, and we actually want to do an intervention where we take into account a fact different from what is in the world, and then want to answer a query. If that is done, given all the interactions that might exist, what is the answer to that? So that's the topic we choose to discuss today, right? So let me start with my visuals, which is the slides on counterfactual methods in artificial intelligence. Okay, here we have counterfactuals in artificial intelligence is the presentation for today. Okay, so I've given you the overview. So the topics in counterfactuals is first the role of counterfactuals in artificial intelligence. We'll begin with what are counterfactuals and how can they be used for explanation. And then we get into a three-layer causal hierarchy. We move from probabilistic queries to causal queries to counterfactual queries as a three-layer hierarchy. And then we move on to a wider topic, exogenous and endogenous variables. These terms are well known to people in some fields such as economics, where endogenous variables are variables that we measure and exogenous variables are variables we don't measure, but they do exist. We are aware of them. So how do we deal with these probabilistic models where some variables are actually measured and the others are not? And in order to deal with both endogenous and exogenous variables, we end up defining what are called as mechanisms and response variables. We'll see what those definitions are. That leads to what are called as functional causal models. So these are not just causal models, but functional causal models, which have built into them these things called response variables into them. And how we answer queries using those, and how these probabilistic graphical models or causal networks using both the current factual causal network as well as a hypothetical causal network based on the particular intervention. The two together are called twin networks. We'll talk about twin networks and how one can work with both of them together to answer fairly complicated questions. Okay, so let's begin with what are counterfactuals. Counterfactuals are contrary to facts. Counterfactual thoughts in psychology. So this is kind of a depressing thing to talk about, counterfactual thoughts in psychology. What if I hadn't been speeding, right? You ask that question, whether you would have got the ticket if you hadn't been speeding. I could have saved maybe a few $100s. Or what if I had not been wearing seatbelts? Oh, wow, you could have had a casualty. And so these are called counterfactual, which are not kind of that useful in human thinking, saying, what's the point in talking about something that didn't happen? It may seem pointless, but they naturally arise in several settings. Here are natural counterfactual examples. In the courtroom, when they're arguing a legal liability, and they would ask a question, did the driver's intoxicated state cause the accident? That is, would the accident have happened had driver not been drunk? They want to answer this question so that they can pin it down on the cause of this accident was the driver's drunken state, right? Legal liability case. You want to answer that question, yes or no? In treatment and diagnosis, we are faced with a car that does not start, but the lights work. Will replacing the battery make the car start? All right, so we're saying here is a scenario where we want to change the battery to a new one and want to answer that question. If doing that, will it have any effect or not? Like we could ask something that is useless and ask, we could obviously say that won't make any difference, but we're asking about something like battery. But the lights work, right? So what is the probability then? Okay, here's another treatment and diagnosis question. Patient did not take the prescribed treatment and did get well. And we wish to determine the probability that patient would have gotten well had he complied with the treatment. So here again, we are asking a counterfactual, did not take the prescribed treatment. What if he had taken, you want to guess as to whether he would have gotten well. So these are all interesting, difficult questions that lawyers and doctors may be facing. And how can they take advantage of some techniques of reasoning which is the kind of forte of AI, right? Reasoning through complex data to be able to answer such questions. What does it take to answer these things? So let's begin with what are the types of questions? Questions in English, interestingly, questions in any language, they begin with the same kind of sound. Like questions in English, they all begin with WH or H. So who is this person? What is this flower? When did America become independent? Where was the Declaration of Independence signed? Why did Americans want independence? And how did America become independent? These are the kinds of questions. By the way, every language has some syllable associated with questions. Like in Latin, it's Q, Q-U-O is a sound for every question. Quo vadis or Kel or whatnot. French is like that too, QU. In Sanskrit, it's the K sound in Sanskrit. And many South Indian languages like Kannada, Telugu, Tamil, they all begin with ya. Every question begins with a ya. Like that. Questions begin in the same way. But those are all standard questions. Who, what questions could easily be answered using a probabilistic model, such as a deep learning model. Who is this person? Based on all the features, we say this person must be so and so. Or what is this flower? This is a hydrangea, right? Based on all the features, the petals, and so on. When did America become independent? A simple database lookup might do that job. Or where was the Declaration of Independence signed? Simply a database lookup or a Wikipedia lookup could do that. More complicated questions are why? Why did Americans want independence? Some AI methods such as causal reasoning might be needed beyond machine learning, which is largely looking at correlations of data. More general AI would answer these kinds of questions. Or how did America become independent? It might be an AI type of answer. Well, these kinds of questions and more of the causal questions can be arranged in a table where we have three levels: association type of questions, and intervention type of questions, and counterfactual type of questions. We call them as queries. Association question, typically seeing what is this flower? How would seeing X change my belief in Y, right? How would seeing a particular shape of the tail of a dog maybe? And what does a symptom tell me about a disease? So just a mapping from symptoms to disease. And what does a survey tell us about election results? This is the kind of thing, association learning. This is the stuff that deep learning largely does. Y given X, right? What's the probability of Y given X? Intervention is probability of Y given do of X, Z. And here we are saying, what if we set this variable to a particular value here, and Z are the other variables involved? We are doing some intervening. What if I change it to X? What if I change the shape of the ear of the dog to something drooping? What would happen to my, talking about the type of breed of dog it is? What if I do X, in some kind of action? What if I take aspirin? If will my headache be cured? What if I ban cigarettes? Will cancer rates go down? So these are called as intervention queries, and which involves doing and intervening. Counterfactuals are specifically changing to a new X prime with an output Y prime. And we are asking, this is actually given X prime now, there's a known ones. And what would a new X provide for a Y? Okay, so X prime, Y prime, which is the other way around here. This notation is the original is X prime, Y prime. For a given input X prime, we have output Y prime. Given that, what would happen if we change that to X and Y? So imagining or retrospection, why? Was it X that caused Y? What if I had acted differently? Was it the aspirin that stopped the headache? Would Kennedy be alive if Oswald had not shot him? This is like one of those counterfactuals. What's the point in asking such a question? What if I had not been smoking for the past 2 years? So again, this is a psychological type of thing. May not be that useful because it's not the case. But as we saw in certain situations, these counterfactuals are of value. So these are the kinds of questions. And you can just imagine, what does it take for an AI system to answer these questions? Association, yeah, we can have deep learning do that. Intervention, maybe if we can introduce intervention into a deep learning model. What about counterfactuals? What does it take? So we look at what these questions are, how can they be modeled, and how can they be answered. So to lead to counterfactual queries, let's begin with causal queries. Causal queries discover causality by introduction, thus ruling out mere correlation. So those are useful in the learning stage. When you construct the Bayesian network, we want it to be a causal Bayesian network where A causes B, in which case it is A arrow B. Whereas a simple probabilistic graphical model, it doesn't matter whether it's A arrow B or B arrow A. A causal one would say A arrow B because it's A that causes B. And also, how do we structure it like that, making sure that A causes B, not B causes A? So we have causal queries by using intervention. We can say, does rain cause umbrella, or umbrellas to be open, or do umbrellas to be open cause rain, right? You go about, if you can change the input by causing it to rain, then you can see if the umbrellas are open, then you can say, oh, there is the causality. And the other way probably will not work. Anyway, that's causal query. Counterfactual query is a different type of causal query. We already have some information about the true state of the world and want to inquire about the state of the world had we been able to intervene and set the values of certain variables. It could be one variable or it could be several variables. A very profound type of counterfactual query: would the US have joined World War II had it not been for the attack on Pearl Harbor? Okay, that would involve a complicated, causal network, which talks about the cause and effect of wars, and what if there was an intervention, what would have happened, and so on. That's the type of historical question that we could possibly ask. So this sounds too profound, counterfactual explanation in AI, but it turns out it's got a mundane use. Explanations are useful for various reasons. When we get into explanations, if life is impacted by a decision, right? So you want an explanation if it is such a major decision that impacted your life, or if you want to challenge the decision. Particular loan was denied, you want to challenge it. Feedback to fix input. Oh, that's useful for an engineer saying, oh, that is an explanation. It behaved like this, so I need to do something else. Fix bugs. So that is also a kind of explanation that is useful to fix bugs in software, or to comply with laws. Certain laws in Europe require explanations for any decisions made financially. Counterfactual explanations are a particular type of explanation. Users prefer counterfactual explanations to case-based reasoning, which is example-based. So case-based reasoning would be, you were denied a loan because your loan is like these other loans that we denied. It's like that. That's kind of a example-based explanation. Or saying credit score was too low, which is why we denied the loan. It is less helpful than a counterfactual explanation that says, if you had increased your income by 10K, or if you had a master's degree, you would have got the loan. So that would be a counterfactual. It is not the reality. And we are saying, what if we had done that, you would have changed the decision. So counterfactual explanation of a prediction, in machine learning, you can say it describes the smallest change to the feature values that changes the prediction to a predefined output. So we are largely familiar with machine learning for classification, for a program that identifies handwritten characters, or a program that identifies animals or transportation modes and celebrity faces and so on. And what small change in these features, X1, X2, X3, could be slightly changed that would completely change the prediction, right? So that would be a counterfactual explanation. If that was slightly different, it would be. So it's an explanation of the prediction. Example of counterfactual explanations. Classifier rejects a loan application based on the feature vector income, credit score, education, age. Those are the 4 features that went into the loan application. Explanations are, why was the loan denied? is one type of explanation. The other one is what can be different so loan will be approved. That is the more proactive and counterfactual. Latter, that is the counterfactual one, is the basis of a counterfactual explanation. What changes could be made to feature vector to end up on the other side of the classifier decision boundary? Increase income by 10K or get a new MS degree or both. So people have recently tried out this in feature space. In this way, counterfactuals in feature space. So let's say we have a feature space based on features X1 and X2, like this is income and this is the education level. And we have the blue region is positive where loan will be approved. And this yellow region here is the region where the loan will be denied. And let's say we have a particular case where we have this blue point on the denied side. And the counterfactual explanation can be thought of as what is the smallest change we can make to this point that it will end up on the other side. So here are two paths that are shown. This one path is going right into the blue region, this red point. And this green point is also in the blue region. So we can take either path. One of them maybe goes along the surface or the contour in a multidimensional space, whereas this one is directly heading towards the closest point through the body of this surface of this data. And so we can say both of these are counterfactual explanations 1 and counterfactual explanations 2. And we could argue that the counterfactual explanation 1 is more desirable, that it requires the smallest change in the feature of X1 and X2. Like we need to change X1 by a certain small value here between these two and X2 by this amount. CF2 would require a larger change on X1, but a smaller change in X2. Anyway, so one of these would be, or both of them could be a counterfactual explanations of why your loan was denied. This can be mathematically formulated as counterfactual explanation as optimization. Even this can be stated as an optimization problem. And say the problem is to minimize distance between counterfactual data point X prime is counterfactual, and original data point X, subject to the constraint that classifier output on the counterfactual is the desired label Y prime belongs to Y of all the labels. So we can state this as a optimization criterion in two possible ways. The first one says argmin of X prime, that is the counterfactual data, and this is the original data. The distance between the two, D, is as small as possible, subject to fx prime equal to y prime. That is, the new data point x prime should be classified by the neural network, which is a function f, to give you y prime. And that is the label that we desire. That's the label that we want. That's one way of saying it, subject to that. Or one can combine this constraint using a standard Lagrangian formulation. We could say this is argmax x prime, and there's a lambda that's coming in, which is some kind of a factor, how close that fx prime should be to y prime. Fx prime is on the other side of the boundary, and y prime is the desired class. How close should it be? We're trying to square that here. First term encourages classifier output on the counterfactual to be close to the desired class. Simultaneously, we say d of x prime, which is second term forces counterfactual to be close to the original data point. So the label should be right, distance should be right, minimize those. And so this could be thought of as a particular loss function in learning to explain. So one issue with these kinds of explanation is that one can have several explanations, right? One can have, if only you changed your degree to an MS, or if only you changed your income by 10K, you would get the loan. Both are reasonable explanations, and one can end up having many explanations because of many features. Counterfactuals are indeed human-friendly explanations because they contrast instance to focus on a few feature changes. What is this fewest? And we are asking that. but they still suffer from what's called as the Rashomon effect. Rashomon is a famous Japanese movie directed by Akira Kurosawa, which tells the story of the murder of a Japanese samurai. And the story has several characters in it, a priest, a farmer, and a woman who's known to the samurai, and so on. And one ends up asking each of them who killed the samurai, and each of them has a explanation of what led to the death of the samurai. Each story explains the outcome equally well, but the stories contradict each other. So none of them supports the other. So I think the story ends up with not a final conclusion as to who killed the samurai. There are multiple explanations. Same can happen with counterfactuals. So we don't have here a samurai being killed, hopefully not with a car driving on the road. It could well be a Rashomon effect. What killed the person on the road or caused the accident. There could be multiple explanations, multiple counterfactual explanations. So this can happen with this approach of minimization, right? All right, we now go into the symbolic approach to counterfactual. There has been a lot of work done on this area in economics and so many other areas. And let's see what they have to say about counterfactual reasoning, right? So they want to see, what, in this case, if you change some value, what would happen? So that's the approach we're taking. We're not asking to find the best possible explanation, but if we make a certain counterfactual, what is going to happen? So that's the kind of approach. So it has to be put to use in the same way as the earlier machine learning or the deep learning approach. So the correlation approach is P of y given x. Probability of event y equal to small y, given that we observed event x. This is the correlation approach, which machine learning and deep learning are great at doing. Causation is the next challenge. Probability of event y, given that we intervene and set the value of x equal to x, and subsequently observe event z equal to z. So these are all the other variables. So we'll show that this do of x is different from simply x. And counterfactuals is more complicated. X and y are the input-output relationship. And we're asking probability that Joe's salary would be y prime had he finished college, given that his actual salary is y and he had only 2 years of college. So his actual salary is y. Supposing he had 2 more years, x changed to x prime, then will y prime, what would y prime be, right? That's a counterfactual. So there's a difference between each of these, and counterfactuals in some way capture causation as well. So here is an example of inferring answers to causal queries. It's an example, a classic Simpson's paradox example is taken up here to talk about inferring answers to causal queries. Simpson's paradox example is that probability of a cure given that one took a particular drug is greater than probability of a cure given that one did not take the drug. So C1 means cured, C0 is not cured. D1 means taken the drug, D0 means not taken the drug. So this probability of cure given drug is greater than 57.5% to 50%. It says this is 57.5% here, 50% here. This sounds like you must take the drug so that we can increase the probability of the cure. Well, it turns out that if you look at conditionals, probability of cure given taking the drug, condition it also on G, that is the gender is equal to male, is in the same scenario is less than not taking the drug G equal to male. It's 70% to 80%. So it is saying, while overall it is saying that you must take the drug, this is saying for males, you must not take the drug. So without taking the drug, you're worse off than without taking the drug. What about for females? The same data set says in the female, taking the drug, the probability of cure is less than without taking the drug, 20% to 40%. What is happening? It's called the Simpson's paradox example. And this can be explained with with this intervention, using a causal network. It's a causal query here. So here we have a table, probability of C given D and G, that is a cure given D and G. There are 4 combinations, D0, G0 to D1, G1, and the cure is C0 and C1. These are the probabilities that we just saw earlier on entered into this table. 2 of these add up, 0.8, 0.2, 0.6, 0.4, 0.3, 0.7, 0.82. So the appropriate query to answer in determining whether to prescribe the drug is not simply this. This is not the query to ask in terms of whether to prescribe the drug or not, but rather P of C1 given do D1. And this says you need to evaluate this probability. And that probability is a method of evaluation which takes into account a trail that exists between drug and cure that goes through gender and cure. So when you say C1 given to D1, you got to sum over, like marginalize over all values of G of C1 given D1 and G and probability of G. And that is how you have to factor in this particular thing called backdoor trail. And so the answer to P C1 given to D1, which is shown by this network, is calculated by entering these probabilities from this table here. And it is saying cure given D1 is 0.45 and cure given D0 is 0.6. So what it is saying is not taking the drug has a smaller probability of cure than not taking the drug. Therefore, we should not prescribe the drug. That's very interesting, that you can go wrong by not factoring some third variable gender. This doesn't bring into the third variable gender into the play, because gender is having an effect on both taking the drug and on the cure. That's what's being factored in over here. All right, so that's the presence of, we can say the gender, if it is explicitly identified, then it becomes what's called as an endogenous variable. If it is not explicitly identified, it's referred to as an exogenous variable. Counterfactuals need mechanisms. Causal model is a graph of causal progression. So that's what a standard causal model is. It's a Bayesian network where we go from one node to the next node. It's a causal progression. The value of each variable is selected in order based on parent values via a causal mechanism. So there is a causal mechanism. A causes B, B causes C, and so on. Details of this causal mechanism are implicit. Assume that variable X induces a distribution P of X, given parents of X, right? So causal query is answered as a probabilistic query, which we just saw. You have to take into account the pathways. This may not always be possible. We may need to reason about governing mechanisms. So there is one more level of complication that we bring in here, and this is referred to as mechanisms. Second reason for understanding mechanisms. So there are 2 reasons to look at the mechanisms. One is certain causal queries may need this governing mechanism, but they're also needed to answer additional types of queries, counterfactual queries and certain diagnostic queries. So we just saw the example of a device going wrong. So to answer such questions, where we are asking a question whether if I replace a particular part, will it perform? Will it be repaired? So there are counterfactual queries. Certain diagnostic queries can also make use of these mechanisms. So the intuition for a counterfactual query, so where we are coming from is that we want to preserve as much as possible between the real and counterfactual worlds. We have a real world model in a certain way. In a counterfactual world, we are taking some fact and removing its dependency and saying we fix it. Mechanism governing each variable provides reliable inferences about the true world, so as to preserve as much as possible when reasoning about counterfactual events. So a mechanism will define governing each variable. It provides more reliable inferences about the true world. All right. To look for ideas of response variables and mechanisms, let's start this famous example again. We have transcripts of a student in a course. There is a grade A here, and so the grade is read by the recruiter and provides a job offer, join our team. So we can think of it as a probabilistic model where the variable grade takes on values A minus, B plus, and so on. And job, yes or no, right? So maybe this is A, B, C, and this is yes or no, or this is just A and B, and this is a yes or no. Example of a need for mechanism. So continuing with this model of grades, let's, for simplicity's sake, let's not work with many valued grades, but high and low, two grades. So G0 and G1 are the two grades for the G or grade. J is the job, J0 and J1, where one did not have the job offer and one has the job offer, right? So let's say are binary valued. Let's say irrespective of the grade, the job was all 50-50, all right? So there is one possible scenario. Counterfactual query. Gump received a low grade and he applied to Acme Consulting, right? And he was not hired. Let's look at this. We're talking about mechanisms and why we need it. Think about the scenario. So he got his grade, applied to Acme Consulting, and he was not hired. Now we ask a question. Would Acme have hired him had he managed to hack into the registrar's computer system and changed his grade to high? All right, so this is, supposing it just went and changed the grade from an C plus or whatever to an A, would he have got the job? It's a counterfactual query. Two models and different answers. Consider two models. Gump applied to Acme and he was not hired, right? So there could be two underlying models that determine the kind of answers he's going to get, both with two equally likely populations of companies, all right? So equally likely population of companies. And let's say first model. First model is they are in a not, 50% of the company are not hiring mode, always reject Gump. And the other model, the other one is that they're desperate to hire anyone regardless of grade, right? Regardless of grade. So Gump was not hired, all right? So Acme is not hiring, all right? So changing grade is useless because they're in a not hiring mode, right? And so there's no point in saying they would hire anyone regardless of grade. And in this case, I was not hired. So it just means that this company fell in that group and it's a rejected Gump. So if you change the grade so Acme falls in this group, and so his application to Acme is no good. So changing grade won't make a difference. Second model, companies are highly selective. Hire only if grade is high, or hire underdogs. Hire only if grade is low. So strange company. So a company that hires only if grade is high, and the company hires only if grade is low. Why would somebody want to hire somebody whose grade is low and pay low salary? All right, so they have something in mind. Gump was not hired. Gump was not hired. So changing grade makes Acme hire Gump. So in this model, Gump would be hired. So what we're saying is, so should Gump change his grade or not? It depends on what kind of company Acme is. If it is not hiring more, there's no point. And if it is a highly selective company, then there's a point in changing the grade. So different answers to counterfactual queries depending on the model of the world. So the answer to the question, should he change the grade by hacking into the registrar's computer system? It depends on what kind of a model the company is in. If it is the first model, it's pointless. And if it's the second model, yes. So we need to know something about that model, which is what leads to this idea of mechanisms and response variables. This also occurs before we define mechanisms and response variables. This also occurs in troubleshooting a broken device, troubleshooting why your car.
Professor, we didn't hear you.
Professor, you're muted.
Okay, here we are. Okay, you're all still here. Great. Good to see all of you are still there. Okay, fine. Troubleshooting a broken device. So we're talking about how this idea of mechanisms and response variables become useful in troubleshooting a broken device. Failure due to a component.
We don't see these slides, and I think that the
Oh, that's
recording
right.
has been
That's right. I
stopped.
need to redo the sharing of the screen. And here we are. Share it. Okay, there was a temporary internet cut there. Okay, it's okay now.
And the recording is also not working right now.
What's that? We need to slideshow. Yeah.
I think.
No, it's recording.
Oh, it's recording. Okay, good.
It's okay now.
Yes.
Okay. All right. Very good. Okay. Okay, we'll continue where we left off. Okay, all I'm saying here is that this idea of mechanisms and response variables are useful in troubleshooting. We'll come to that later on. So let's now talk about what are called as exogenous variables and endogenous variables. So let's watch this small YouTube video. I need to. Okay, all this is a coin tossing video. I hope you can see it. Okay, you saw the coin tossing video?
Dear road rivals, charging.
Okay, can you see my slide on exogenous variables?
Yes.
Yes.
Okay, all right. So we just saw the coin tossing. Okay, anyway, that was not an important one, just to introduce a little bit of media into it. So coin toss depends on exogenous variables. What are those? Coin rotation, forces applied, air movement. So you can say that what does the coin toss depend on? If you knew all these variables, that is what is the speed of the coin rotation and what were the forces applied to the coin and what was the air movement, given all these variables, coin toss is no longer probabilistic, it becomes deterministic. So it's only a question of specifying all the variables. So exogenous variables are there, but coin rotation, forces applied, air movement, but they are not something that we measure and incorporate into our model. So let's talk about exogenous versus endogenous. Exogenous variables are external. The way to remember which word is which is exogenous is external. They are unmodeled latent variables. We just saw about a coin, rotation, forces applied, air movement. Here is another example of Gump's hiring, right? Let's say there was a particular student called Gump, and he went through our student network, and the question now is he has got these grades in the courses. This is his SAT score, and prior to that, that was his intelligence, and that was the difficulty of the course he took, and so on. And then now we have a particular grade, and the job offer depends on grade and SAT score. Will he get a job offer? Well, his hiring depends now on the company goals. Poor Gump has applied to this company, and the company goal may not be to hire more people. Funding level, did they get enough venture capital money to hire people? Number of applicants, if they received hundreds of applications, that might be hard. And it might depend on the tie that Gump wore for the job interview. If he had a tie that had pink elephants on a green background, who knows, he might get the job. So these are all what are called as exogenous variables. Color of the Gump's tie is an exogenous variable. Endogenous variables are what we choose to include in the model, right? The endogenous are things like, grade and SAT score, right? We abstract away from exogenous variables and focus on their effect on endogenous variables. So we don't explicitly model them, but we are cognizant of their effect. So we launch into this fairly interesting idea of response variables that do some justice to these exogenous variables. Let's say U is the entire set of exogenous variables affecting outcome of J in a causal model G to J. Grade can be G1 or G0. Job can be J1 or J0. And here are UJ. These are the exogenous variables. And what are the variables these UJ can take on are what are called as mu J values. And we define what these mu J values. So they affect the causal outcome of J in a causal mode. J is a deterministic function of G and U. We say that this job value J1 and J0 is a deterministic function of G. This is a random variable. And there is also this U, which is a member of this U here. Small u is a member of capital U. And G belongs to, small g belongs to capital G, and J takes on value Fj. So this is a deterministic function Fj of G here and U here. So what is this U? Mappings between G and J. U induces 4 possible mappings enumerated as, so there is these mu J's. What are these mu J's? Mu J's are G1 maps to J1 and G0 maps to J1. So that's the kind of mapping here. What this is saying is whether the grade is low or high, always higher. That's what this function is. Second function is G1 maps to J1 and G0 maps to J0. This is a rational recruiting, which is a high grade, higher, low grade, don't hire. The third of these mappings is G1 to J0, high grade, don't hire, low grade, hire. This is the underdog cases. That is, we only want to hire, those who got low grades. High grades, we don't hire them so that we can pay them less salary. The fourth model is G1 to J0, good grade to don't hire. And this one is G0 to J0. So irrespective of the grade, never hire. So these 4 cases are always hire, rational recruiting, underdog cases, never hire. So this says we have these 4 possible values here. And we furthermore say we're going to have a probability distribution over these 4 possible values. What's the probability of always hire company, rational recruiting company? Maybe rational recruiting is the highest probability. Underdog may be lowest probability. never hire some in-between probability. There's a probability distribution over all these types of mappings over here. And this is a random variable, this is a random variable, but together they get combined in a deterministic function, fj, combines these two values. So this u function, which lists all these, is referred to as a response variable. uj is a response variable. We can think of, there would be a response variable ug associated with grade also, but it has no parents, so there is no interesting thing going on here. UG values are simply G1 and G0, the same as the grade. So that and this together end up defining the value for the job variable. So we have now explicitly pulled out the values which require mapping. It talks about what are these UJs? They show the mapping between this and this. Parents are needed here in order to define this, right? So it says based on the value of the parent taking you to which value of the child, right? So it requires both of them. That's what a response variable uj is. So this is a new variable we introduced, and we call it u as this is exogenous variable. So the effect of the exogenous variables are somehow captured in these things, okay? So it's kind of outside of the picture, but modeled in this way, which is looking for this mapping. So response variable definition. So what is the formal definition of response variable? Here we go y, which takes on values y1 through ym, and x, it takes on values x1 through xk, and then there's a u of x which maps these values y1 through m to some x1 through xm values, and those together are going to be mapped into these. So let variable x have a set of parents y, k equal to val of x, all right, k equal to val of x over here, and m equal to val of y. Response variable for x given y is a variable ux, whose domain is a set of all possible functions mu y from val y to val x. That is, let y1 through ym be an enumeration of val y. For a tuple of generally not distinct values x1 through xm, we use this notation as a little cumbersome, mu x. So those are the mu's values here, each of which is a mapping from the y values to m values, and to denote a function that assigns xi to yi for I equal to 1 through m. So it's mapping these values, although these are only k values, but there would be the explicitly corresponding values of x. The domain of ux contains one such function over each tuple, giving a total of k to the power of m functions of this form. All right. So there is what's happening here is previously we needed a table which was called a CPD, conditional probability distribution table. Now we are talking about response variables. The number of combinations becomes much larger. A functional causal model C over endogenous variables x is defined over two sets of variables x and u. Endogenous variables x, each variable has parents of x. So this is all a formal definition of a functional causal model. So we're saying a functional causal model has two sets of variables. Chi, or the x, corresponds to the regular variables in a probabilistic graphical model. U are the response variables. So endogenous variables x, response variables u. And each variable x has parents of x, a response variable ux for each x, and each variable x is deterministic. And it's all being said in a formal way, what we just saw as an example. And here we are giving an example of a more complicated network, which has 3 levels here. It comes from a clinical trials. Assign the patient to a placebo group, or they administer the drug group, and then the treatment that is given, and then the outcome of the treatment, right? So we have every variable creates a response variable. As A creates UA, T creates UT, and And then there is outcome creates UO, and there is a parent-child relationship, which is kind of defined over here, or response variables as given in the along by the endogenous variables here. So functional models, functional causal versus causal. So we are now causal models and functional causal models. What's the difference? Standard causal model provides only a CPD for each endogenous variable. So this is a standard causal model. Grade leads to job. And there are M values of grade and K values of job. So we define a table. This one requires only two values, 0.2 and 0.7, and the others are 0.3 and 0.8. They're added up, right? So either that way. So it requires two values, two independent parameters. A functional causal model needs K to the power of M minus 1 parameters. Functional causal model where we spell out each of the mappings between the grade and the job, it requires K to the M. In this particular case, K to the M minus 1 leads to 3 independent parameters, whereas this one required only 2 parameters. And of course, this goes up exponentially as we increase the values of K and particularly of M. So the functional causal model for clinical trial, again, is shown here. This is the same network we just had in the previous slide. Assigned treatment A does not influence response O directly, but only through the treatment T. UT has 4 functions, always taker, complier, defier, never taker. All right, so just like we had the company situation. And here we have outcome, always well, helped, hurt, never well. Okay, and there are sample CPDs that are given for each of these UT and UO. So the data may provide you with these kinds of probabilities, and that results in a joint distribution of UT and UO that is given here. So these are the CPDs for PUT and PUO given UT. Multiplying those, we get these probabilities. So functional causal models are useful for intervention queries. And the causal queries concern the effect of intervention. If Gump sets grade to A, will he get job offer? Answer is obtained from mutilated network. So what we do in the mutilated network is that variable's ancestors are removed from the network, and we fix the value with probability 1. To answer them, we need to consider the effect of latent variables on observed variables. Functional models. So we talked about causal models and functional causal models. What's the difference again? Causal models have only CPDs. Functional causal models have response variables included. Functional causal model C is a causal specification including latent variables. To answer intervention query, mutilate the network, eliminate incoming arcs, and then do inference. But statistics are only over observable variables, no distributions over response variables. Yet they are of value as they can provide partial answers to causal and intervention queries and provide bounds on the probabilities. So functional models can provide bounds on the answers. Functional causal models useful for intervention queries. Causal queries concern the effect of intervention. To answer them, we need to consider the effect of latent variables. So functional model can provide bounds. And relating variable, X and U, each conditional probability X is a sum of some subsets of probabilities or response variables. So what about these original conditional probabilities? Each conditional probability can be written in terms of the probabilities we assign to the different mappings of these UJs that we just saw. So these two probabilities together account for 1, these two together, these two. This is just like in the case of the company, Gump applies to Acme. So those probabilities consist of several types of companies. Those probabilities are all being added here. So the summary of these constraints on values of queries is observed endogenous variable probabilities impose constraints on response variable distributions. While we may observe endogenous variables, those probabilities tell you what kind of distribution you can have on the response variables. These in turn impose constraints over values of queries of interest. Using possible values for distribution over the response variables, we can obtain bounds on the values of queries of interest. So this leads to an example of where we can give bounds on any query. Does medication improve chances of cure? Standard clinical trial we're doing. The naive answer is probability of O1 given T1 minus probability O1 given T0. That is, without treatment, you have a certain probability of outcome. With medication, there's a certain probability outcome. How much better is the outcome probability than before? Then that's the naive answer. It's incorrect due to compliance cure correlation. So there can be a correlation. If treatment compliers are sicker, then cure rate in population with for which T equal to T1 will give pessimistic estimate of treatment efficiency. So the correct answer is the intervention query. So we say where you are requiring them to take the treatment, and then the outcome, is that better than the outcome when you're requiring them not to take the treatment? This measures increase in cure probability between a patient who was forced to not to take the treatment and one was forced to take it. So this is known in the medical community as the average causal effect of T on O, denoted as ASTO. Right. So on an average, does this forcing people to take the medicine give a better cure rate than forcing people not to take it? You don't want to use the standard probability model because there can be artifacts about who's actually taking the medicine. So can one get these bounds on this ACE if not exact values? In general, linear programming can be used to find bounds on ACE. In the simple problem, closed form expressions for these bounds can be found. ACE TO is greater than or equal to this probability. ACE TO is less than or equal to this probability. So the difference between these bounds is you can add the two together. And these bounds, like I say, subtract one from the other. These bounds are known as natural bounds. Natural bounds, okay. So functional causal models can be used to answer counterfactual queries. We now see how to do that. And similar issues arise in a diagnostic setting where we reason about probabilities of events after taking a repair action. So the idea of twin networks is we are reasoning in parallel about two different worlds, the real one, which is the left side here, and then the counterfactual world, which is shown over here. In the counterfactual world, we are removing one of these links here, showing that it is mutilation here. Both are governed by the same causal model, except one involves an intervention. Critical property, the desired output for a counterfactual query is that it involves minimal modification to the true world. A patient in study took prescribed treatment and did not get well. Would he have gotten well had we forced him to comply with the treatment? Formally, this query is written like this. This is a cure. This is the intervention query. That's why it's O prime. T equal to T1, O equal to O0, and do T prime. So we are intervening here. Formally, this query is written in this way. Intuition says if you change nothing in the counterfactual world, outcome should be the same. And clearly, we cannot simply generate a new random assignment to the variable in the counterfactual world. And we want the treatment to be the same in both worlds. And response variable makes this intuition precise. So a response variable for counterfactual in a functional causal model summarizes effect of stochastic influences influencing endogenous. And moving to counterfactual world, choices remain the same. So consider a counterfactual query. Patient didn't take treatment and didn't get well. The query is patient well if complied with treatment. Answer, assume patient assigned to treatment. Assume in helped category. Both of these are conserved in the counterfactual world. If that's the case, under these conditions, we obtain that the patient would have recovered had he complied. And we made some assumption about the value of the response variable here. In general, we don't know value of response variables. However, a functional causal model specifies a prior distribution over their values, and resulting posterior can be used for inference in the counterfactual world. And this shows the complete derivation application to clinical data. Trial is randomized, med unavailable outside group, and the joint distribution is the same one we just saw earlier on. Query is this one. Certain values in the original world and then in the counterfactual world would have gotten well if complied. Answer is you have response variables. UT have these possible values. UO can be these possible values. Conditioning on the joint distribution posterior, you get these 4 probabilities. And outcome determined value by U naught. In this case, it is when the patient is helped, these 2 values here, and corresponding to 0. Now, using computed posterior, the answer is 4 plus 6 over 13, 10 by 13, indicating that the patient would have gotten well if you had insisted on his taking the treatment. Counterfactual twin network is we put together the, let's see, a functional causal model over endogenous variables X and corresponding response variables U. And a counterfactual twin network is a functional causal counterfactual twin network causal model over variables X union U union X prime, such that all these things hold. Basically, we're talking about the 2 networks we saw earlier. To answer counterfactual queries for original causal model, construct twin causal model. Answered query as an intervention query in that network in exactly the same way as any functional causal network. And this is showing, again, the clinical trial example. To answer this intervention query, use a simple intervention query in the twin network, specifically mutilate counterfactual networks so as to eliminate incoming arcs into T prime, condition on our evidence, and simply run probabilistic inference. So using inference in the twin network. Okay, so that's where we are. And so that kind of summarizes our discussion of counterfactuals in artificial intelligence. We started with the idea of where counterfactuals are useful. They're extremely useful in generating explanations, but to generate them, it's a complicated scenario to reason through what we have. So we need to construct a functional causal model, not just a causal model. A causal model would just show the relationship between variables as to what causes what. Not only do we need that, we need a functional model where we create some variables, new variables called response variables, which can be regarded as modeling the exogenous variables that come into play. And such functional causal models can be used to create twin functional causal models in the true world and the counterfactual world. And then we infer through this complex model to answer any counterfactual query. So it takes quite a bit of effort. Now you can think about what it takes, first of all, to do intervention queries in these networks using, say, deep learning methods. And then can we go from there to causal models or to functional causal models or to twin models? So those will be the topics to study next. Okay. Do you have any questions for today's lecture? Okay, if not, we're done with the lecture today.